and this is the lecture series called Math Science Literature and History, organized by CMSA in Harvard University and YMSC in Tsinghua University. Today's talk will be more on more applied side of the math science. Professor Harry Sam will be in charge. Thank you. Harry.
Thank you very much, Professor Yao. Welcome everyone to Math Science Lecture by Harvard University and the Tsinghua University. I'm Harry Shum, an adjunct professor at the Tsinghua University. It's really my great pleasure to welcome Professor Yi Ma of UC Berkeley to give this very interesting talk on deep networks from first principles. I have had the great pleasure and the fortune to have known Professor Yi Ma for many years, and having watched him doing amazing work in computer science, computer vision, and machine learning. I also had the great pleasure to recruit Professor Yi Ma from Illinois to work at the Microsoft Research Asia many years ago. We had the great pleasure working together on some of those work that actually had some relationship with what the Professor Yi Ma is going to talk about. So without further ado, Professor Yi Ma, take it away.
All right. Thanks, Harry, and also thanks to Professor Yao for the introduction, and also it's such an honor and pleasure to give a talk to this audience. As you can see from the title, right? So this actually has something to do with the deep networks. So this is a subject has captured people's imagination or attention in the past few years, both from the practical side and the theoretical side, also even mathematical side. And so this, again, from practical side, I work in computer vision. We have extensively used some of the techniques. And also for, in the meantime, on the theory side, we're also really curious, right? This is actually a lot of these networks and the practice were drawn from the practice, right? We don't quite understand them very well. So today we'll try to take a perspective, maybe offer a plausible framework or program that we can actually understand deep networks in a more principled way. So for a while, since the rise of deep networks, the deep networks themselves has been the object of study, right? And so many papers have been written about the different components or parts of it, and also individual phenomena associated with the deep networks, try to explain its empirical success and so on, right? But for a while, since the pandemic, right, give me a little bit of time to think about, it has been a little bit frustrating to see the gap between theory and practice has never really been bridged, right? We can probably explain one thing at a time, but overall, the practice deep network evolves. There's come up with new tricks, new observations, and somehow theory seems to be chasing what the practitioners are doing. Also, on the other hand, right, despite we may have gained some understanding or knowledge about the deep networks, parts of it, but never has really been able to guide the practitioner to do anything beyond or better, right? Or even just explain what they've been doing in a more systematic way. So this is a sort of what we have been doing the past couple of years and trying to take a new perspective to this problem. After a while, we realized that maybe deep networks themselves should not be the object of study. We should just go back to study what the learning is all about, right? The most two fundamental tasks in data science or even actually nature, right? Animals, or we do analysis of scientific data, we try to cluster data and make sense of the data. We try to classify them. So the question is why? And what do we gain out of it? Turns out that one of the very plausible approach to look at, more fundamental way looking at why we do cluster classification is actually through the data compression. As we'll see today, based on the same principle of data compression, right, we actually give us a very principled objective for learning good representation That's what everybody does these days. We call it a rate reduction. Reduce the coding rate from the whole data set to its parts or to its classes. Once you realize that, we start to realize that the deep networks actually become the means to the end, right? They will arise very naturally, the architecture and operators and so on, naturally to achieve these tasks. And that's actually the one thing I'm kind of excited about this is that for a while, certainly you can start to realize them, right? This start to give deep learning or deep networks a very theoretical, rigorous footing. Although there's still many open problems, especially open mathematical property of this framework we don't understand, but it truly actually opens up the door for serious mathematicians or statisticians, people or theoreticians to start looking at those problems in a very rigorous fashion. Now, let's forget about the deep networks for a second, right? Let's try to think about what we really want with learning from data, right? The fundamental questions we ask about data science. And so this is the very minimal assumption we're dealing with real world data is that we assume the data has structures, right? Maybe belongs to multiple classes. The minimum assumption we make is that maybe each class lies on some no-dimensional manifold, right? For good and bad, right? There could be statistical, there could be finite samples, but in any way, sort of a leap of faith, we assume that those data they are separable from each other, have the distinction from each other, right? Nonlinear manifolds is good conceptual models for that. We'll try to be more precise later. Now, three fundamental questions, right, about what do we do with data. Despite people give them very gazillion different names, right? But really that to begin with, when we give a set of data, the first thing we want to do is to do actual interpolation, right? To figure out who are my neighbors, who look like me, right? Or if my data lies on the same line or curve and so on and so forth, right? It's really the notion of clustering, grouping, or segment data. If we're able to do well on that, the next thing we get a little bit bolder, right? We try to say we can extrapolate now from what we have learned from the existing data, right? If the new data comes in, we try to decide which cluster, which structure, which line it belongs to. That's actually a problem of classification, right? Or extrapolation. Finally, right? Those first two, interpolation, extrapolation, is just data explaining data, right? If I'm allowed to change the data or deform the data, right? Maybe we can build a model for it, fit a line to it, fit a model to it, right? So the purpose of that is we try to find a more compact model to explain my data. And also, maybe I can make the models, different parts more discriminative. That's actually what you heard from representation learning or learning features and so on, right? These are really the three things we do. So far, I haven't seen anything go beyond this, okay, in terms of data analysis, at least the popular ones. So then when deep networks come along, right, a few years ago, says that, well, we start to sort of forgetting what we're really trying to do with the data science. And we actually just say, can we just lump everything in the black box? We give the data and we try to fit the labels. We label them and we try to fit this mapping from the data to the labels, right? This actually has seen quite, empirical success, also even pushed along the technology, right? The problem actually becomes very simple in the sense that I only have to find a mapping, right? Usually represented by a deep network, such that the outcome of that network correlates my label, the Y output, right? The best they can, right? Cross entropy is a very natural or very popular objective to measure that correlation. That's seen a lot of success and a lot of excitement, but then actually there's some big elephant in the room, right? Turns out actually, if you choose, we all know, if you choose a network large enough, it actually can fit anything. You can arbitrarily scramble the labels, you can arbitrarily scramble the pixels of image, you can always fit it, right? And you ask yourself the why that is the case. And we will try to get to that later. And also, even after you fit the label very well, right? There's millions of parameters, millions of nodes in between that you don't really understand what the statistical geometric meaning of those. Finally, even regarding the empirical performance, right? Although despite many people try to convince you it works so wonderfully magically, but actually as a practitioner myself, right? the highly trained engineer, the neural network, deep network, actually are not as good as you think from a mathematical or a rigorous point of view, right? They're actually not robust. They're quite vulnerable. They're not from invariant, right? For rotation, translation, far from that, okay? Even small deformation will actually, the network by output very, very different answers. Let alone, it really doesn't help us to understand the data very much, right? What have you learned? What have you actually extrapolated? So there have been some attempts to try to explain what the deep network is trying to do in the past from the information theoretical actually remaining perspective, right? Optimization, information theory. This is one of the framework people adopt, quite popular, say that maybe the network is trying to, it's a hypothesis, right? It's trying to extract features that most correlate with the label and also throw away all the irrelevant information, right? So hence you maximize mutual information between the feature and the label and minimize the mutual information between the data and the thing. Conceptually, they might be doing the right thing, right? But the point is that they still sort of find out what are just the minimum features correlated to your label, but does not help you understand what the true structure of the data. Let alone this formulation alone is also task and label independent, very highly label dependent. If you change a task, change a label, so is the quantity associated with it. Actually, there's a bigger elephant besides deep network itself, right? There's a very big gap between theory and practice, especially in the information theoretical perspective. We talk about many of the quantities, right? Entropy, mutual information, Kell divergence, maximum likelihood, as if they exist, right? Turns out that when we're dealing with high dimensional data, such as images, the millions of dimensions, right? And those quantities are impossible to compute, okay? They're just, the complexity just blows in your face. Let alone, there's an even bigger issue, right? A lot of the distribution actually are degenerate. The support are zero measure, right? And hence, none of those quantities I mentioned listed up there is not even well defined. Then you start asking the question, what are you computing? Yet every paper in NIPS, they start with those quantities, pretending they exist. Right. Hello? There's some, yeah. So of course, in practice, when people take the theory framework, start to do approximation, simplify assumption, and also even ad hoc tricks and hacks, then suddenly you don't really know, the theory stop to providing any guidance or even guarantee. Actually, this is a problem we realized about 15 years ago when we were trying to do image segmentation, dealing with high dimensional data such as images or face recognition and so on, right? And when we even just making a simplifying assumption that your data lies on linear subspace, let alone submanifolds, right? And turns out those problems persist. And instead of taking the conventional statistical approach, you actually have to take the low dimensionality of your data or the model head on, right? One very useful perspective we found that actually unifies not only the concept, but also the computation is actually compression. I'll give you sort of using clustering classification to give you a little bit of background before we move on to the deep networks, right? So what is clustering? Very simply put, right? So I have data drawing from some mixture distributions. I try to partition them, right? And so of course, the statistical tells you, okay, let's just write model this as a mixture of distributions, right? With different proportion pi, and also each one has a component distribution. We estimate the cluster based on maximum likelihood, which point belongs to which cluster, right? The popular algorithm is called the EM algorithm. Basically just alternating between the estimating the theta parameter of the distribution and also the mixing proportion pi, the membership of your data. Well, this is a nice framework formulation. However, actually in practice, no people actually do this, right? Because the ML maximum likelihood is not even well defined when the distribution are degenerate. So this is about actually I was actually visiting Microsoft research at the time, right? One thing we took a look like, then why ask the question a little bit further, deeper, right? Why do you want to cluster your data, right? You must gain something from it, right? So hence, if the data, high dimensional data, they're actually compressible or they can be partitioned, because maybe if I partition them in the judicious way, I can save the space, right? Hence, a very fundamental criteria to partition or not to partition really is to check if the number of bits or space or volume, whatever measure you take, is to store the data together is more or less than store the data as two different parts or multiple parts, right? It's kind of the whole is greater than sum of the parts. Now, if once you have this idea, you start to ask the question, now how do I measure the volume, right, of the data? So information theory and I think mathematics actually offers all kinds of tools, right? Sort of metric entropy and so on. One thing that is very, very relevant to from a data processing point of view is actually the rate distortion, right? So if you give a set of data points, let's say from a Gaussian source or lying on low-dimensional subspaces, right? So you actually can derive, if I allow a slack, because I have to convert, if I want to save my data on a computer, I have to convert a continuous number to a finite number of bits. So if I allow a slack of epsilon, the accuracy, prescribed accuracy, then the number of bits, binary bits, that can save those data points subject to that precision is precisely given by this expression. We call it coding length, right? You actually can derive this in both two different ways. One is from a purely statistical, probabilistic way, right? By packing the spheres, epsilon balls of space spanned by the source, the Gaussian source, right? Sort of a ratio of this volume between the volume and the volume of the sphere epsilon ball. Or you actually can derive precisely the same formula from a purely algebraic point of view, right? Quantify the SVD of your data, that you don't have to assume any probabilistic distribution. And turns out this actually is the upper bound for if your data lies on low-dimensional subspace. Now, once you have such a measure, then the clustering really becomes compression. Right? The reason I compress, partition my data because I will say bits. That's it, right? We become a bin counter. We count the number of spheres, balls we can need to pack my data, epsilon balls, right? So, turns out, therefore, the partition on the right-hand side is always better, preferred than the left. Why? Because it saves you space, saves you number of balls. And of course, this is providing a guideline or objective to partition the data, but it doesn't solve the problem of partition, right? Which the partition of data itself is a combinatorial problem. But at least this gave you a measure to try, right? Give me any partition, I can try which one is better, right? I can compare. Hence, you can actually do all kinds of greedy algorithms. For example, here we propose one just to merge data, 2 points of a pairwise data, if that allows to save extra bits. It's a highly greedy fashion, but actually works incredibly well, right? To this day, we still don't know why, right? It has really kind of, statistical physics kind of interpretation, right? This kind of compression-based objective function has a natural tendency to help you find the global optimal of the clustering, the partition, right? And also extremely robust to the outliers. You can have 70, 80% of outliers, they still be able to identify those low-dimensional structures that has a higher density in your data. And also it demonstrates very sharp phase transition with respect to the quantization. You give a different quantization, the partition will be different, but it is has a very, very sharp transition, just like what you would see in some of the phenomena in the statistical physics. But for a practitioner point of view, right? Despite we do not understand everything, but it actually gives the state of the art to segmentation algorithms at a time, right? But shortly after that, you probably know what happens. Deep networks hits and everybody starts to do supervised, right? To do labeled segmentation and try to fit the labels. Here is completely unsupervised. And without any heuristic, you just compress your data. You actually get the best segmentation at a time. So that's about the clustering. I mean, the compression help I convince you, right? Compression helps you identify low-dimensional structures. And once we are able to do that, maybe we get a little bit emboldened, right? And if the new data points come along, we try to decide, okay, which cluster, which substructure it belongs to, right? Again, statistics says, okay, let's model this as the mixture distribution. Let's do the maximum likelihood. Or map, maximum a posteriori classifier, right? Everybody does this. Everybody says this, but nobody does this, right? That's actually kind of a dilemma, right? Again, why? Because, what are those distributions? How do you estimate them? It's very not obvious. And also, again, this issue with degeneracy going to kills you, right? This object function is not well defined. Right? That's why in practice, people use SVM instead or use neural networks. So at the time, actually, this is precisely the work with Harry when I was visiting there. We start to look at this problem again from compression point of view, right? So what really allows you, what you really gain by classifying a point to a different cluster, right? You must, that one particular cluster must be better in some way, right? Just tells me why it is better, right? Turns out that then you can measure the extra number of bits you needed to incorporate that data into each of the cluster. Whichever cluster pay minimum extra bits wins, right? This is really sort of the law of parsimony at its very best, right? Just I use the simplest, whichever cluster can explain the new data points with the simplest language, the simplest bits, you win, right? So we call it the minimal incremental codinance criteria. Right. Sounds very basic, even naive at some point, but actually this does the right thing. It's probably even better, right? You can actually show when the number of samples goes to infinity, this actually simple bin counting criteria converge to the best the regularized map criteria. Not only that, it regularizes criteria, not only in terms of degeneracy, but also add sort of dimension-dependent regularization. Which means if the probability between two models are the same, I always prefer the model has a larger geometric dimension. Sort of, has a sort of error on the safe side, right? Kind of tendency. Actually, at the time, we observed something rather interesting, right? I mean, in fact, although this classifier is based on purely data interpolation or extrapolation, but it actually functions as a near structure classifier. Right? We don't see that in other classifiers. K-nearest neighbor will give you boundary. Here, we never see samples on the left-hand side, yet the boundary pretending, the classifier will actually pretend it actually have seen the structure. It's really extrapolating low-dimensional structure all the way to the left, right? Yet SVM K-nearest does not have that kind of extrapolating behaviors. So at the time, we were pretty happy. We sort of, this is something really doing the conceptually right thing. However, in practice, it's not very useful. Why? Well, two things. One, it's still non-parametric. In order to compute this classifier, I need to, using data to compute data, to classify data. Second, if my data here works, remember this measure works very well when you have a Gaussian or linear subspace measures, right? But the real data may not be linear, maybe nonlinear. What do you do? Well, at the time, we try some kernels and so on, right? But anyway, it's a little bit wishy-washy. Conceptually, we know it's doing the right thing, but those are the two issues where you sort of stop from there. Now that brings us back to the modern days, right? Now, well, remember those two issues, right? What if I'm allowed to model the data or allowed to deform the data, find a new representation of the data? Can I resolve those two issues? I have a chance, right? For example, maybe I can fit my data with some more parametric, more compact models now. That's one. Second, if my data start to be nonlinear, maybe I can go through some transformation to make them linear, right? This linearization is, universal in engineering, right? System is nonlinear, we linearize them, right? Data is nonlinear, we linearize them, right? The final, also, maybe if I'm allowed to do such a transformation, maybe I can sneak in something extra, right? From the day one of pattern recognition. If we're dealing with mixed data, maybe we want to separate them as far as we can, right? Maybe we want to make the different structure as separable as possible, right? So this is my wish list. So then when you ask your question, then if you are allowed to do this, what is a good representation? Why neural networks comes along, right? Keep that in the back burner. Now, let's try to be more formal, right? So if I'm allowed to transform my data, however I parameterize it, deep networks or whatever, we'll talk about a more principal way to derive this. But so what's my wish list for the final results, the outcome? Maybe feature of the same class, apple, right, or orange, should be highly compressible, right? They maybe go map to a same linear low-dimensional subspace. Or if I have the different classes, apple, oranges, maybe I want them to be as orthogonal as possible, as incoherent as possible, right? So I can separate apple from oranges. Finally, rather than just fit the label, I want to understand everything, differentiate apples from oranges, not just the one dimension, not just the color, but maybe the shape, maybe the leaves, and so on, right? So how can I find all the features can explain the data that you are different from all other classes? We want the representation to be as diverse, as large as possible. Again, the question is there a good measure for that? Turns out the cross entropy is by far not the right answer, right? There's a work from Donald's group says that if you train with cross entropy, then each class gets mapped to a one-dimensional feature, right? Very minimal. They call it the neural collapse phenomenon. Now, don't forget about the compression, right? If I'm allowed to transform the data through a nonlinear mapping, let's say just for sake of simplicity, think about the nonlinear mapping by deep networks, right? So then the question is, I must have some way to tell how good Z is, right? Well, for all the data together, we know I can at least measure the volume. That's the sort of zero order geometry I can measure, right? So that the rate distortion, the average on number of bits, sort of tells me how large that space is overall. Now, if my data has internal structure, let's say lie on two-dimensional subspaces, I can partition them correctly, then the average coding rate, right, will drop, right? That's sort of, so don't be scared by this expression. This is exactly the same expression, except that the pi just encodes which points in the columns of this Z matrix belongs to the same class J. Okay, just the convenient way to encode it. So I sample belongs to J's class. That's sort of can interpret it as either 1, 0, 0 or probability. Either way works. Right? So hence, really that this quantity really measures the average number of bits. I need to encode those data separately as two classes. Then one very basic idea is that how to measure your representation is good or bad is that maybe the difference between the overall feature and the parts should be the larger the better. Why? It sort of have the tendency that if you give me a space of D dimension, I should use all the space to represent my data, right? So to keep all the information I want, the richness of it. Yet each class needs to be compressed as possible. So sort of the slogan here is that similarity contrast and dissimilarity contrast, right? 同性相吸，异性相斥, right? It's Chinese, says that all the time. This is old philosophy, right? I mean, although those qualities are very basic, very fundamental, and it looks a little bit ugly, but it's actually a very magical property about them. We'll see that in a second. But this is actually very, very intuitive, very, very simple to the bone. Right? What it really does is just we think about the data as a whole, right? The first part is just measure how many spheres, balls you pack the space of all feature spaces, spanned by all features, right? The green part, the average coding rate are in fact just imagine you have two data lies on two straight lines in R2, right? Intrinsically, left and right both are the same. It says my data lies on two lines, and they have similar volume and similar space, right? So I need a similar number of green balls to cover those spaces. However, extrinsically, they are very, very different, right? We have a sort of tendency to prefer the representation on the left. Why? Because it says in this configuration, these two lines are orthogonal, incoherent, very separable, very distinguishable, right? Very discriminative, whatever words you use to describe it. Hence, you can see that what really the rate reduction really measure is actually the space, the number of blue balls is the space in between, right? So the total number of spheres you pack the space and the number of spheres you pack the data, the intrinsic structure, and also the difference, the rate reduction is exactly what's in between. And you want to maximize that, right? Hence, naturally needs to, the better representation will maximize that quantity, the number of blue balls, right? So you can formulate this more formally mathematically, right? The total minus the parts. And now imagine if you just count the sphere blue balls, right? And you say, well, if I just wanted this to be large, why cannot I scale this thing twice or 5 times? Then the number of blue balls will be bigger than the left, right? But then you will cry foul. They say, well, that's not fair, right? Because they're not what? They're not normalized. In order to do fair comparison, you need to normalize the scale. Turns out that that's all there is, right? I mean, people in the literature, practitioner come up with all kinds of normalization scheme, batch norm, layer norm, instance norm, group norm, right? God knows how many other norms they're going to come up with, right? Turns out this is always doing mathematically the same thing. In order to compare two things fairly, you need to have the same scale. That's it, right? And it turns out that all the normalizations are actually equivalent. Mathematically, conceptually, and even algorithmically, they are all exactly equivalent. You only wanted to normalize so that when you compare features learned from different networks or from different layers of networks, the comparison will be fair. Well, the question is that this seems to be a very interesting, intrinsically interesting objective, but would this really do the right thing? Remember, we had that big wish list. Turns out that this miraculously, this does, right? Under fairly broad condition, you can actually prove when your data achieves the optimal configuration, meaning that maximized rate reduction, then the data belongs to two different groups will be exactly on subspace that are orthogonal to each other. Not only that, within each subspace, the data will distribute it almost isotropically, right? They will try to expand that direction of the subspace, not just the one, right? So we sort of in terms of the slogan, we fixed what Aristotle says, right? We don't just want the whole to be bigger than the sum of the parts. We want the whole to be the maximally greater than the sum of the parts, right? That gives me the best representation of the data. And there's some, literature people actually try to do this similar way, but for the interest of time, I'll sort of skip those, including people try to do contrastive learning, contractive learning. All the terms has been there, right? But turns out they're sort of basically just using one side, one part of the heuristics that the rate reduction is trying to achieve, right? Both expand and also compress. But rate reduction expand what needs to be expanded and compress what needs to be compressed, rather than doing things in a heuristic fashion. Now, finally, that you can see that the one thing good about this, for example, how do we model the mapping? I haven't said anything about this, right? But for now, let's, for the sake of just have fun, right? So let's just model this, pretend that this mapping can be modeled by ResNet, any of your popular networks, right? And we train with this rate reduction objective function, or we maximize rate reduction. The difference is now, is very different now, is that you can monitor your training of your network by monitoring three physically, geometrically, statistically meaningful quantity, which are the coding rate, right? You can actually see how things get expanded and how things get compressed, right? Each of the, and also how their difference grows, right? It's kind of very interesting. Now, to compare with cross entropy, everything else is fair. The same data, the same architecture network, and the only thing difference is the objective function, right? You replace cross entropy, the label fading entropy, with the rate reduction for the data. And you start to see that very interesting thing. This is on CFAR 10. There's very practical data sets, CFAR 10 data sets, right? And you can see that you start to see this 10 classes. It has 10 classes, airplanes, apple, orange, birds, ships, and so on. You can see the feature you learned. This is actually a confusion map between the features, right? The cosine similarities, cosine angle. Right? You can see that this gives you beautifully clean, there's no crosstalk between the features you learned from the 10 classes. And this is what you get from the conventional neural networks with cross entropy. Also that you can see that each class, right? If you compute remember we're embedding every class into a subspaces, right? You can compute the principal component, right? They're not actually collapsed into one dimension. They're actually widely, evenly spread in that each subspace, right? About 10, 12 dimensions. You actually can see that plot the images along each of the principal component directions, right? You can see that this automatically, the coordinates in each subspace actually encode interesting information, statistics that's never given to you through the label, right? They actually discover really statistically common things within your data. One thing that you leave away from fitting the label is that you actually can, the algorithm is right, object functions try to learn what's statistically common, right? Even you have these labels, right? There's 10%, 20%, all the way to 50% of completely corrupted labels, right? And yet the algorithm, the rate reduction will learn what's common for each class, will ignore those mislabels. You can see it has a very graceful degradation against the label corruption because it's not actively fitting try to explain every single label you give to it. Yet instead of trying to explain data as a set. And also, if you don't have a label, you can do self-supervisor, and that's what people very use. This also gave you the state of art. For the interest of time, I will not get into this. It's just because I will talk about a more principled way of doing the self-supervised learning just in a second. So now the question, are we happy, right? So you start to ask your the question, we will be able to replace label fitting with something intrinsic, right? Rate reduction, which is, sphere packing, sphere counting. And also it's more, you can argue that the object function is more interpretable, right? And also indeed the feature learned, because we're trying to encourage data, final feature on orthogonal subspace, they're geometrically or statistically more interpretable. And also we see of the result, right? The learned feature are indeed more robust to label corruption at least, right? However, there comes with a big but, right? How do you model this mapping? Where does this come from, right? Why 18 layer or 35 layer or 100 layer ResNet? Why ResNet, right? Well, it's still black box, right? Also, from a mathematical point of view, you guys say, why a deep architecture network? Why? Why cannot be? So some people say, oh, because it's a universal approximator. No, it's not. The Fourier series is the universal representing. Or the single layer network is also universal representing. Why don't you use that, right? Or what about some graphs, right? Nobody explained this, right? Just keep using it. And also, by the way, what are those linear and nonlinear operators in the network? Why do we have to interleaving those linear and nonlinear in that way, right? Nobody really quite, some people try to explain from a functional approximation point of view, but why? There are other choices too. Why have to be this one? And also from processing images, right? Nobody actually explained to me, right? We use convolution all the time, but actually in modern neural networks, it's always using multi-channel convolution, meaning that you stack multiple channels convolution and actually doing a 3D convolution, not a 2D convolution. Why? There's nobody explained that. The question really is, can we replace that black box with a white one? The good thing with be clear about what you want is that you couldn't care less, right? I couldn't care less about deep networks because I know if I'm confident this is the objective I try to optimize. Once I can optimize this, I'm done, right? I solved the learning problem. Who cares about deep learning, right? Or shallow learning, right? But if I can solve this problem, find the global optima for this problem, I'm done, right? So then the question is, can we just directly optimize it then? It's some kind of weird log determinant and non-convex object function, right? There's expansion, there's compression. Well, let's just use the gold standard, right? The gradient descent. If we have some non-convex problem, we don't know what to do with it. Let's just do the gradient descent, right? This is the minimum we can do, right? We compute the gradient and we descend, push the data points around, see under what configuration we can actually maximize this reduction. As soon as you do that, right, the gradient of the first term actually looks like this. The second term looks like this, right? You can start to realize that there's some structure to start to evolve, right? To emerge. Right? This is actually just some matrix hit your data, and this is another matrix hit your data. Well, if you know the membership for each class of the data, right? Within each class, that you apply a linear transformation on each class of data. And basically the gradient looks like this, right? Linear matrix multiply, and plus some membership. That's the form of the gradient. So what are those operators? For people who are familiar with statistics, you recognize them right away, right? They're exactly the autoregression, right? Not only that, so basically multiply each data point is exactly computing the residual of you auto-regress each data points with all the other data points in your data set, right? As a regressor, right? So however how well they explain this data, the residual gives you that. So if the residual, if you wanted to explain the data points using data points belongs to the same class, the residual tells you how good that gets explained. If there's still a big residual, what do? You try to push it back, right? You try to reduce that residual. Also, if you want to expand the data, you find the direction that is not explained very well, you actually further expand that, right? That's what happens to the expansion. And turns out that this is actually very fundamental now, if you think about it, right? Those operators sort of decided by the data themselves, right? And keep in mind that this autoregression doesn't require anything else, doesn't require even models of their data, right? Doesn't require linear subspace, doesn't require Gaussian, doesn't require any mathematical model. It's just data explained data. Right? Why? Think about a zebrafish, right? Think about an animal. They don't know about the Gaussian distributions. This is something they have to do, right? They only see the data themselves. Now, schematically, if you think about it, really they're trying to do, I have to do some data points, right? I'm trying to push them using gradient, using the rate reduction as a measure, follow the gradient flow of the rate reduction, and push them in directions so that they will be orthogonal, they will be linear and orthogonal incrementally, right? So this is actually, of course, all the gradients are well defined on the data if I know the pi, right? Remember, the second term, you needed to know the membership of the data points. But what about the points on the other part of the space? You don't have the pi. They're not training data. They're not given to you, right? So what do? Well, extrapolate. Remember the minimum equivalent continuous. You solve a approximate classification, right? The CZ precisely computes the residual for you. You already have the residual. How well each point, how far from each cluster, right? So you have that at your disposal. Just build a soft mass classifier, right? And to approximate this second term of the gradient. So you end up with a mapping of the entire feature space. You can deform the space and based on guided by the training data. By the way, this is one particular way of, once you know what you're doing, you will try to approximate the membership. There's gazillions ways you can approximate it, right? If you restrict your data points to be the first quadrant, use all 4 positive features, then this quantity you can show very easily. This can be approximated as some Renault operator, right? So basically, instantiations are many, right? But you know exactly what everybody is computing the same thing, right? So the only question to realize that if you write down we're able to compute the gradient descent, right? Let's just write down the algorithm for computing the gradient descent, right? It's k l plus 1 equal to zl plus this is the step size of gradient descent. This is exactly gradient, right? I computed the expansion part, compression part. Of course, remember we have to normalize everything to a sphere or choose your favorite normalization scheme and you stick with it, right? So then once you realize this, you actually end up with, you take the iteration of an algorithm, you get a compositional maps of this form, right? Linear, nonlinear, and also projection, right? We're all engineers, we like to draw diagrams. If you just draw diagrams, you end up with a diagram like this, right? From the previous iteration, you pass through some linear operator at identity. This is the gating, sorting, routing, and then add them together, normalize, pass down to the next iteration, and you're done, right? This is exactly a gradient ascent algorithm, right? But actually gives you a network, right? If you recognize this, is exactly give you a network. And you can actually compare with what other people come up with empirically, right? This is the first residual network, identity plus some residual part. By the way, surprisingly, right, we even know those are the residuals of the autoregression. We actually know precisely what they are. Later on, people find that if you add the parallel channels to the res network, you get better performance. Right? Do you recognize the similarity in the megastructure? They're exactly the same, right? However, something surprising, right? Here, this network, everything is computed in a forward construction fashion. There's no backpropagation. You don't need to train anything. All the E and C are not randomly initialized. You don't even need to go from the last layer and try to backpropagate. You don't do that, right? You don't have to do that. And this is a comparison to the latest Google, right? Google, they have thousands, tens of thousands of GPUs. They can do whatever they want. But this is the latest 1.7 trillion parameter they call switch transformer. And this is the architecture. And if you take a look, right, they're exactly routers, and also there are 4,000 parallel channels. They call them experts, right? Here we know exactly what they are. There are different classes for apple, oranges. They're experts for apple, oranges, ships, and birds, right? So, however, the meta structure is exactly the same. They're just bigger, right? Also, they randomly initialize everything. They have to train everything from backpropagation. Here we don't, right? And does this work? Yes, it does, right? It actually works even better. I mean, in some sense, right? So, people at the one time, people call that the deep network needs to be deeper, better. My student has some fun, right? They build a network with 2,000 layers. It works, right? You start with Gaussians, like this is a simulation, right? 3 Gaussians on a sphere. And you can see that after few hundred iterations, you precisely squeeze every part to a low-dimensional subspace and also make the subspace orthogonal, right? It's really doing this nonlinear ICA for you automatically. And finally, for computer vision folks, right? We want more, right? This is just vector, right? You can see schematically this already works very, very well. What about in images, right? We actually want the mapping to preserve more information, right? Have more structure we are, especially for geometers, right? For computer vision people, for example, we want to do recognition. We want to recognize the digits regardless of our rotation and also position, translation. Right, for simplicity, I consider translation on the torus, right? Think about this is everywhere. So then the question becomes, if I have the data, I can transform by some group. I want the feature after the mapping that should belong to the same equivalent class. Okay, that becomes a rigorous mathematical statement, right? So despite all the engineering happens these days, right? People try to convince you, how wonderful neural networks are. Actually, they're not that good in terms of this task, right? There's 2 recent papers. You can force in with simple transformations. You can, generalize very poorly to small image transformations, right? Because you don't test on every translation. People just augment 5, 10, right? Different translations or rotation, and in the training, and also only test on those 5 or 10 augmentations, right? What if you wanted the transformation, the classification to be rigorously invariant? Then you need to embed all the rotations, all the equivariant instances into the same subspace. That's it, right? So basically, all the samples, their group transform, the equivariant instance needs to be mapped to the same subspace. In our cases, can we map them to the same subspace? Just to do it simplified, let's think about a single one-dimensional data, right? I have a sequence of signals. I wanted to, all the translated version are equivalent, belong to the same class, right? So I can arrange those, all the translated version into columns of matrix. This becomes a cyclic matrix, right? Now, mathematically, the problem becomes very, very simple. Can I map group of all those translated versions into the same subspace, squeeze them, compress them into the same subspace? Well, reduction precisely doing that, right? So now if you, instead of just to compress the original samples, you also compress all the circulated versions. Suddenly you realize that, remember those linear operators, expansion, right? Those gradient, linear operator associated with gradient, expansion or compression, they automatically become convolution. So this is the difference. You do not stipulate, you want to use the convolution to achieve equivariance or invariance. Here is the task of compression, determines that. Like the data stipulates that, right? The greedy way of compress your data automatically give you the convolution, not just the form, but also the value. Also, but there's actually, once we realize this, we realize something fundamentally interesting now. There's actually trade-off between invariant. You cannot have both. There's something goes against each other. So you cannot assume you want the separability to 2 classes of signals and still want all the invariance you want, right? For example, if I have one class data contains a delta function, if I'm allowed to translate everywhere in the world and also do arbitrary superposition, I can generate any signal in the world, right? At least a discrete one. Well, then you cannot separate it from any other subspace. It's not a subspace for the whole space. So what is really required become a necessary assumption. Why I can separate the fish from ducks? Because actually I'm not allowed to do arbitrary shifting and superposition. They're not going to give me natural images. So turns out you actually assume your data actually is sparsely generated from some patterns, right? Some dictionaries. And the superposition can only be sparse in the sparse coding space. So instead of separating X, you really should be separating the sparse codes. But how do you get sparse codes? Well, there's gazillions ways of getting it. One simple way to get them, just to hit your data with multiple random or pre-designed filters, right? Just convolve your data with different filters. Well, there's many, many different ways to design this, right? This is not the best way, but as long as your X has no dimensional structure, turns out a random filter is not that bad, right? Theoretically, right? And once you convolve, then you sparsify. You know the Z needs to be sparse, so you just make it, do some thresholding, random or soft thresholding, whatever. Everything goes actually here, right? As long as you get a decent hold of the sparse code of your data, and then compress them together. Then use reduction, right? Using gradient descent to compress all the cyclic version of the sparse code together. magically, right, those linear operators can actually do a very careful study. They give you multi-channel convolution, right? So even you start with independent convolution K1 to Kc, right? As long as you start to do gradient descent, right, the E operator and C operator precisely going to mix those channels to you have, because this inverse, when you compute the inverse, that precisely introduce crosstalks between those channels and give you multi-channel convolution of your data. So just to do a simple comparison, right? People actually have tried to build the convolution networks from scratch, right? Using wavelets, for example, and try to, also take the modular of the outcome, and so that you achieve approximate invariance, translation invariance, and so on. But there's two very fundamental difference here, right? Here, when you build the network by design, you don't know what filter to use. Hence, you use a complete basis, right? And that explodes in your face. Next layer, every branch needs to use this complete basis. Basically, the number of filters you use just explodes with an exponential in the number of layers. You can only build 2 or 3 layers. Second, even you have a theory for wavelet basis for 2D images, but what about a multiple channel? Right? I have thousands of channels. There's no way you can design those filters, the multi-channel filters from any principle there, right? But the ReduNet network give you all that for free. Not only the forms, but also the channels, number of channels stays constant, because they only care about the data that you've given to them. Right? You only care about apple and oranges. They don't care about the bananas or pineapples, right? I mean, they're only designed to optimize the differences between apple and oranges. And by the way, mathematically, there's something very quite interesting, right? Remember, when we're computing this E and C channel, we need to compute the inverse of this gigantic matrix, right? If I have n pixels, C channels, that's like the Cn by Cn. It's a humongous matrix. However, this is a matrix actually with a very, very interesting structure, this inverse, right? It's on this identity process circular matrix, blocked circular matrix. We know circular matrix can be diagonalized by Fourier transform, right? Therefore, once you do the Fourier transform, those matrices in between become blocks of diagonals, right? Or through permutation becomes diagonal block diagonal, right? Then computing the inverse of matrix of this form in the spectral domain is only cubic in the channels, but linear in the number of pixels, right? Instead of cubic in pixels. Right. So this is actually a very interesting thing. This fact alone put a very black and white distinguish between the spatial domain and the temporal domain, right? A spectral domain and the temporal domain, right? There's a fundamental advantage. You computing or learning those filters, learning those operators in the spectral domain. Okay, this is the mathematical evidence for that. Actually, in neural networks, right? In natural neural networks, in visual cortex, actually neural encoder transmit information precisely in frequency. They don't compute it in amplitude, right? That's why they call it spiky neurons. And maybe this provides one explanation why this is the case, because this is really the most economical way to do computing. And for the first time, you actually can write down the entire deep networks, right? All the parameters, all the operators, all the architecture in the white box, actually in the spectral domain. Right? They just become an optimization algorithm. And you start to see the elephant. Finally, you can see the elephant, right? In the past, we care about dropouts, normalization, overfitting, all the different pieces. Everybody think it's, a deep network is optimization, it's a functional approximation, it's dropout, it's statistics. Actually, it's no, right? It's just a signal classification problem, a representation problem, right? And once you realize if your goal is to learn such a linear discriminative model, that everything becomes necessary. Okay, they're not necessarily sufficient, but they are necessary, right? You need a sparse coding. Your data, different classes data needs to be separable. Okay, otherwise you cannot do it. Or deep network is nothing but an incremental way, grading way of reduce the rate, so that make different parts linear and make different parts discriminative. And also, if you want to be invariant, right? Just like our very visual recognition, then you better compute it in the spectral domain, right? Because that saves you big time. Convolution, normalization, nonlinearity, they just actually come along, right? Just in this, achieve this goal through a greedy fashion. Does this work? Finally, we start to see really you can build neural network that is truly invariant. Okay, you can here we no longer just augment the rotation at 10, 5, whatever number of rotation of your choice, of your convenience. No, we actually build the networks with every single rotation, and we test that way, right? So you actually around all the degrees, you can see that the similarity after the separation, they become purely orthogonal. Actually, by the way, there's no mathematical proof for that, why you can do that. This is just results, right? Start with 0 and 1. 0, 1 is usually a hard one. Also, it generalizes to 10 digits, right? Actually, you can do this with 10 digits, and you get 10 orthogonal subspaces for all the translation or rotation, okay? Not just a few augmented ones. And this is for translation. It's the same story, right? Here, now we translated the image, the object, everywhere on the torus, every single pixel, and we separate them. And we also tested them on every single translated pixel. Rather, so you no longer have this kind of issues, right? Can be fooled by poor small image deformation or things like that. Yeah, here you really get orthogonal subspaces after the deformation. Transformation, map the 10 digits to 10 orthogonal subspaces with all the translated versions. By the way, see, as I said, right? So the whole Redu network is constructed in a forward fashion. We don't do any back propagation, but that doesn't say you cannot. Okay. See, each optimization, each layer is doing the optimization. You can stop wherever you want. But if you stop early, the network is not going to be good enough, right? Maybe the final result is not good enough. Then what you can do? The architecture, the metastructure is exactly the same as ReduNet, as the transformers, right? Do the backpropagation if you have the resource. If you are Google, right? If you have extra few thousand GPUs to burn, go ahead, right? With the labels, do cross entropy, do MCR, and backpropagate. Of course, you will improve the performance. Hence, backpropagation is nothing just by fine-tuning the models you get. Right. Also, that the Redu network, the forward construction already gave you initialization. You no longer have to initialize your data from random samples, from random values, right? Actually, they gave you very good initialization, close to the global minimum. Right. It's much more effective. So last few more minutes, I'll try to conclude. I mean, I think the one of the goal of this try to hopefully motivate some, not just engineers, actually probably there's more problem associated with mathematics. So from this talk, we can see that if you realize, right, the learning, doesn't matter we're doing the data clustering in an unsupervised way or in the supervised way, right? Before, about 15 years ago, what we did is actually optimize the second term, right? Remember that the second term, right? We fixed the x is fixed, but we try to minimize the pi, the membership, right? Which points belong to the same group, or there's new points comes around, which cluster, which segment it belongs to, right? This is minimize the colimits. This is minimize the incremental colimits. But regardless, they're just instantiation of data compression. Now, when you allow, now we allow fixed pi, okay, given pi. If we allow to learn z, we allow to transform z so that make them better, quote unquote, more compact, more linear, more discriminative. Then the rate reduction, the difference between the whole and the parts become a natural intrinsic measure for that, right? It does push the data into orthogonal subspaces and so on. And all you have to do is just to do a greedy descent. Of course, you can borrow any neural networks to approximate, right? To model the z theta. But a natural way to do this, just you might as well just follow the gradient flow given by the rate reduction. That gives you the deep networks, the structure, the architecture, the operators, linear, nonlinear, and even their values. Okay, so that's actually very much provide a rather unifying way of looking at what we're doing with data science or data analysis. Just to do, for people who are familiar with neural networks, right, the practice of neural networks in the past few years, let's just highlight some differences, right? Compared to conventional deep networks, since it's been 60 years, 70 years, right? The left-hand side has always been the case, right? It's fitting the label. Architecture, we try and error. People even do random search these days, right? or initialization is random or pre-designed with wavelets and so on and so forth. But you don't know which one to use. Basically, you try. And then, of course, after you design the black box, the only thing you can fine-tune it through backpropagation, right? Even you tuned it, even you have trained it, it's still a black box. You don't know what each node is doing, right? And that's why if you have a new task comes in, a new class comes in, you retrain through backpropagation. There's a phenomenon called a catastrophic forgetting, right? So basically, you learn how to differentiate apple and oranges, but if the same network ask to learn pineapple, you train with the labels of pineapple, then the network will suddenly forget about how to differentiate apple and oranges, and you don't get that in a ReduNet network, right? Even the representation, even after all the training, what are those features? What are really the statistical geometrical meaning? You don't know, right? So in this compression-based framework, we know the objective become rate reduction. Bean counting. We're counting the beans, right? The number of balls packed in the space. The architecture is just nothing but iterative optimization, right? Then any ideas of optimization goes here. And also the network is constructed forwardly, right, from the data, right? It doesn't preemptively strike all the signals, but just the data provided for it. And also you can optimize this forward, backward, either way. Turns out forward is more natural. There's no evidence in nature. Individuals that learn things from backpropagation. There's no mechanism for that. But forward is very, very natural. And also become entire white box networks. And the final representation is invariant subspaces, right? It's a very elegant, beautiful mathematical object to study. And there's all kinds of open problems. We realize that. By the way, we're very, very just scratching the surface about the theory in terms of understanding. Why? For example, suddenly the work we start to realize even the phenomena, right? We see why just minimizing second term against pi works so well, right? We don't know, right? This phase transition behavior, we don't know. And why even this one is very, very robust to label corruption, up to 50%, 60%. It's very, very robust. Why? There's no rigorous justification for that either, but it's a very persistent phenomenon we saw. And why this gradient descent will reach the global optimal, right? Desired global optimal. There's no guarantee for that, okay? There's no study, but empirically works very, very well. And there should be a theory for what are the configuration of your data, what is the optimization path, allows you to reach the plausible optimal solution. And also for the first time, right, once we start to realize the connection between deep networks and the low dimensional structure, there's some very nice trade-off, interesting trade-off between sparsity and invariance. We never realized before, by the way, before this work. I've been working on sparse representation all my life, right? Try to represent every single one as a sparse code. But I never really realized that, right? There's a trade-off between, so you can shift the signal everywhere you want and allow superposition. And that is actually not in contention. Actually, that is in contention with the sparsity or separability of your data. Finally, right, so I talk about the two sides of the story. One is the fixed x optimize pi, or fixed pi optimize z, right? Well, in reality, if you have data, just like a zebrafish, or you don't have the label, nobody gave you the label, right? And can you just learn structures, both good clustering or class information, as well as a good representation, so that in the future, you can separate the prey and the predator, right? Can you do that automatically? That may be in terms with an optimization problem, you do this both jointly. Right? That's something also we're working on. Also, if you don't care about mathematics theory, you care about algorithm architecture, there's tons of problems, right? For example, we know this convolution neural network arises from the gradient descent, but what about additional structures? Actually, it turns out there's a lot of redundancy, C channel, E channel, shares a lot of common structures. That's what we're also working on. And also what in practice, people using sparse, separable, or short convolution, under what assumption of your data or a model that those convolution has additional structure, we don't know. And once you realize deep network come from optimization, the layers are doing optimization, then all the tricks, all the ideas we have known in years of optimization comes to help, right? You can do acceleration for the optimization. That will introduce skipped connections, right? In practice, people do find that's helpful, right? But how to do this in a systematic way? And rotation translation works, but what about other groups, right? Deformation, homography, 3D rotation, and so on and so forth. We don't know. Right, this is leave all for future. But the idea of compressing data, all the equivalent class data together, that's a very, very fundamental geometric problem in my mind. Also, everybody trying to understand deep network from a kernel point of view. Actually, you're staring at a kernel right in front of you, right? The log determinant of this covariance, to compute the log determinant of the covariance matrix, you don't need the covariance. You don't need the, you only need the pairwise inner product. You only need the Euclidean kernel, right? Turns, of course, if your data is nonlinear, you can replace that with any kernel of your choice, either designed or learned, right? Turns out that that's exactly what people do. Now they call them self-attention, okay, from Harvard, right? So it's just computing similarity among the data, right? I mean, Google, I mean, people have, you know, the machine learning, I have a joke about this, right? Henry Compere says, mathematics is the art of calling different things the same name, right? I mean, the machine learning has a tendency to call the same thing different names. That's unfortunate, but that causes a lot of confusion. Here is really, it's basically just computing similarity among your data, and so that you get better information about your membership. That's all there is, right? You're not doing anything magical. So finally, there's a lot of extensions you can think about, right? Here we talk about the vector case or group invariant, translation invariant case. We talk about the convolution. But what about other dynamical graphical structures? People extension to RN recursive neural networks, also to graph. I believe that has a lot to do with it. However, regardless of what you do, right, the principle of compression should play. It's always at the heart, right? How do you compress your data with dynamic structure or with graphical structure that respect the structures? Just like what we did, convolution neural network is doing compression that respect the translational invariance. Okay. And also that once you realize the network is doing nothing but identify the low-dimensional structures, subspace or sparse structures, and you can potentially make your estimator much more robust, right? For many, many years, people try to fix the robustness of neural network, but they don't even know what you want the network to be robust against. Against a line, a plane, a curve. Nobody talks about it, right? Then what are you talking about robustness then? And also that here we talk about mapping the data to the Z hidden spaces, right? To truly measure how good this encoding is, you need to take a generative model. How can the Z space can map back to the original space, right? And finally, there's something really interesting. After our work, I get a lot of papers from neuroscientists that actually told me that those characteristics, right? We see that in that elephant, the beginning with the visual cortex doing sparse coding. And also in between, the visual cortex is computing in frequency. Finally, in higher order of your infernal temporal cortex, the primates remember identities, objects, or faces. They encode them with a subspace. Turns out those neurons are precisely encoding the coordinates of each instance of faces in that subspace, not prototypes, not memories. There's some work from Caltech recently. That's kind of really interesting, kind of see that this kind of characteristic that purely derived from mathematical principles, right, start actually has their manifested into the nature, right? Maybe nature is smarter than us. So this is the final references, right? You can see some of the work traced back to the work I did with even Harry back in 15 years ago. Really the notion of compression play a fundamental role in clustering classification, and also that it also helps, the compression helps with looking for better optimization representation, in this case, through the rate reduction, right? And also the networks, deep networks, is nothing but a means to the end, right? To help you to find the representation, find the compression for your data. And there's also a new textbook sort of capture this in a broader sense. And just like deep networks, we're just started. I mean, don't try to compare ours with the 10 years of practice of deep networks yet. I mean, there's we're facing Google, Facebook, Microsoft has engineered those networks to death. But where we have a humble starting point, and you can find some of the early code. It's purely white box networks. GitHub, Google Lab, Jupyter Notebook has all the examples, simulations or real data, and so on and so forth, right? And we'll keep maintaining them, and they probably gets enriched, and you expect that it will evolve very quickly in the next few months. really, I like the way, looking at this, this gives a constructive way of deep networks, right? What you cannot create, I really don't understand, right? So, now this gave you a way to create things. So if you forget about everything I said today, I truly hope you remember this one sentence for the rest of your life, right? So it's a deep convolution neural networks. The architecture, I'm not talking about training neural network. The architecture themselves are iterative optimization scheme for compressed data, right? Thank you very much. That's all.
Well, thank you very much, Professor Ma, and it's a very, very exciting talk. And I personally very much like the elegance of MCR2, your framework, how you put this in this, the overall framework of compression. So for the audience, we have still about 18 minutes for questions. And please, as Ryan said, put your questions in the Q&A box. So I'm going to start with the first question from the audience and Professor Ma. So the question is there a systematic way of picking the number of Redu layers? Did you just need to pick the number n such that you assume n iterations of ascent will be sufficient for convergence?
Yes, so that's a great question. I get this a lot. So already that this framework already distinguish the previous, right, neural network design. Usually people try, right, 18, 30, and based on the size of data, based on the number of classes and so on, and people try and error. At least in this framework, the iteration, each layer is actually doing optimization for you. Hence, just like any other optimization algorithm design, we want to make that process converge as fast as possible. So here in the Redu network, we only use the gradient descent, arguably the most naive vanilla version of optimization, right? In the rich literature optimization, you can do acceleration, right? Even you use gradient descent using first order method, you could introducing acceleration, right? Here we just doing the gradient descent here, right? Then that will actually start to introducing skip connections, right? Just for example, less drops acceleration, right? And all kinds. And also even second order method, if you wish. But that will involve computing probably more computational intensive operators, right? Basically, all the ideas of accelerating the iteration, make the convergence faster helps here, but I leave that for future. Second, and at least also because this is doing optimization, right? And also you're monitoring the object function directly, the rate reduction. So you can just stop, just like what we normally do, play with any, when you stop when you start to getting diminishing returns by adding a new layer. The good thing here is that Harry is very fundamentally different from the practice deep networks. Deep networks, you have to try, even you add a new layer, you have to retrain that entire network, and see how it works better or not, right? Here is so much more economical. You just add another layer. The previous layer you don't have to touch. You add another iteration of the operator, which is computed precisely from the previous layer. You don't have to retrain everything. You can tell if you're getting diminished return or not, if you need that extra layer or not. Even for that point alone, this program is already very rich. Third, finally, of course, if your iteration, number of choice of iteration gets limited, right? Say I can only save, fine, maybe my algorithm takes 100 iteration to converge to get a beautiful subspaces, orthogonal subspace, but I can only stop at 30. Why? Because of my memory. I'm using a bad computer, right? I can only save 30 layers, or especially some, I only have that memory. Then what do? You still can fine tune. This first 30 layer, the structure is already there for you. Those parameters already initialized for you. Of course, you can use the label data or using the MCR object function still to fine tune the parameter of those 30 layers. Nobody is stopping you from doing it. So in that sense, it's consistent with any other neural networks people are doing with any other neural networks currently, right? And also you gain from it. Why? You don't do random initialization, right? Those data are already, those values are already initialized. And One thing you probably didn't realize, I want to highlight this is a little bit. You only need one sample per class to get the structure of the network as well as the initialization of all the parameters. If you realize that, right? So basically the structure of the network and even some decent parameter is already, basically I only need one example for apple and orange. I will be able to construct the network with arbitrary depths so that in the end, the feature extracted for this one apple, one orange will be orthogonal. You can do that already. If you have new samples comes in, of course, go ahead and fine tune it. So those three perspectives probably answer your questions, right? You can take either one interpretation, and either you can optimize the improve the optimization algorithms, or make them converge faster, or you can fine tune it. And also it helps you monitoring how good the results are. And you have actually stopping criteria, very objective stopping criteria for the number of depths. No longer, unlike before, right? You really have to try.
Yeah. So yeah, I really like, in particular, your third points. You almost hinting that, the practical way of using your approach, probably will be some kind of combination of
yes.
Doing the forward network first, almost like initialization for the backprop, if you really want to fine tune. Perhaps for both the quality, accuracy, and also the efficiency, a practical way of applying this will be a combination of both forward and backward.
And I want to add to that. You don't have to actually, in fact, you don't want to do backpropagation. Now we realize that now. The reason we do backpropagation is because we have no other choice. The only way you do backpropagation because you're treating the whole process as a black box. Now, then you get the consequence of catastrophic forgetting. If you add new classes to it, you train the whole entire network. You don't know which part is doing what, right? Yeah, when you train on pineapples, you're going to forget about the apples and the oranges because you're treating as a black box. Now we have a much better alternative. We have a white box. We know exactly what part to optimize. When there's new classes comes in fact, you should always do forward propagation. And they're actually equivalent mathematically, probably even more efficient. So also in nature, right? That's why some of the neuroscientists tend to get excited because they was telling me that they start to see this is sort of giving them a new way to look at those are the computational mechanism. They say there's a chance that that's what might be the nature is implementing. Right? In the zebrafish, you cannot wait until like 20 layers and then try to backpropagate. No, they can never do that. Maybe for species level, yes, that's called the reinforced learning, right? Bad individual gets selected out. But individually, my structure is already determined, right? You only get to incrementally learn your environment, your object by absorbing the data. And you don't get to this global optimization or supervised learning, right? Everything has to be done in an incremental fashion and also in an adaptive fashion. And the forward propagation, forward optimization is much more natural than the backward.
Yeah, I see your points. I think it would be even more interesting as you start to have some more detailed studies of comparing how accurately can you really do those tasks, especially as you said that deep networks have been fine-tuned by many people over a decade.
Yes.
So I am very excited to see your future work and other people's work following up this. So let me we have more questions coming in. Let me just ask you a follow-up question by the same person in the audience who asked the first question. So the question is that in this new interpretation of layers as iterations of optimization, is there a way to think about the width, not only just the depth of a layer in a classic neural network? So what are we really doing from the optimization lens when we increase the number of neurons in a given layer?
Beautiful question. This is a great question. I'm showing this slide. This is something truly fundamental. So Redu network, you guys know, it's doing something very objective. You give me input data. I'm just trying to push those apart. Okay, linearize them, compress them. However, what is the input to the ReduNet network? The code. This is actually what happens in our visual cortex, right? We're filtering out images with those filters, and we're presenting those multiple channels of responses. Now the question is, see, however many channels you use here remains constant, right? The rest of the operator gets fixed, right? Unlike a scattering network. Here, once ZL has 1,000 channels, those remain the same number of channels. So the depth here is the same. Now the question is, what is the number of channels you need? So this is, I get back to the fundamental question in the sparse coding, right? What is a dictionary? How we most compactly representing our data, right? This problem is actually separated from what the Redu network is doing, right? It's really how do I represent my data as a sparse superposition of some templates, right? That has something to do with how the natural images are composed of. How many bases do I need? There are many ways to do this, guys. First of all, there's a branch called the dictionary learning. Basically, we learn those dictionary to represent X by some sparse signal. I actually worked on that a lot. Actually, people working on ICA should know this literature, right? This has something to do with the ICA and so on. Now, that's a learning. I learned those dictionary. Then we'll find out how many bases that do I need. The second thing is the approach is that, well, like wavelet people, well, let's just use wavelets. We pretend they're good enough, right, for images and so on. So we just use them. We just fix those as a certain number of wavelets, right? Those are just a wavelet basis. I hit convolve, I try. So that's another approach. Is sort of lazy approach, but actually is not that bad. Is that we know if we only need to assume those X has low dimensional structures, right? Has this kind of low dimensional sparse structures. Hence, the theory of compressive sensing tells us, in fact, as long as you are making that assumption, your data are indeed, it has low dimensional distributions, then random filters are not that bad to preserve all the information about the structure. So in practice, actually, all the experiments you saw in this talk or in many of our papers so far, we actually just use random filters. About 50, sometimes 5 or 50 or 100 random filters, that 100 channels. So the true number of channels needed will depend on what is the low dimension, how low the dimension of the structure you're dealing with. You're trying to separate, you're trying to recognize. That's unfortunately or fortunately will be data dependent, task dependent. But as a general principle, all you need to do is to assume your data are indeed sparsely generated or has those low dimensional structures. I hope this sort of answered that question. Yeah. Mm-hmm. That's a modeling problem. Yeah.
Yeah. Okay. So we probably should move to the next question. And so the question is that how does the lottery ticket hypothesis fit in this compression framework?
Well, I don't know the details of lottery tickets, but I can assure you, actually, I'm going to talk about something we're working on now. By the way, guys, here we're still talking about very vanilla Lice and Danny situation, right? We can do some greedy deformation. We can get the data pushed towards the linear subspace, right? Fine. At the core, that's what we're doing. But what if the data, the topology of data is very, very complicated, right? I mean, not allows you to achieve this in a global for all the data, for all the distributions. What do you do? Well, then there's a randomness or partition of your data needs to be done, right? So different initialization, maybe I sample different data, I have a better chance to capture the global topology or local topology of the data better, right? And so random initialization with different kind of random assignment, feature selection and so on, or initialization of the group membership may have end up with a different, if I'm lucky or if I'm actually have a chance to do that. This actually leads to another point of view, right? Why do you settle with a single neural network? Remember what I said, right? This framework allows you to build your network, both the structure and the parameter from one sample per class. Well, you can build a forest if you want, right? Basically just says that I just randomly subsample my data. I build a classifier for just for those prototypes. I can aggregate. Now, how do you aggregate? From ensemble for all those. Basically you build gazillions of rich classifiers and everything. Right? There's many ways you can stitch them together, right? As long as you know you are doing this picture at heart, right? You can do different pieces first and so on, and then stitch them together. Nobody is stopping you from doing that. And of course, the more judicious way you do that, you may gain. Your method might work better. Definitely, there's sort of random guess or sort of randomness in the beginning will actually give you some benefits later. Allows you to have a better chance to converge to a globally more plausible solution for the classifier for the representation. Right. Hope that addresses the issue, but that's something definitely needs for future investigations.
Yeah, that's good. And let me ask you probably one more question that in the related work you actually mentioned that some related work by your friend Yang LeCun and others on contrastive learning. Can you just elaborate a little bit in the relationship, how you see, MCR2, is actually more comprehensive than the previous work, on contrastive?
Oh, yes, that's a very good question. So, people are, let's say, in fact, not just but Benjo has a work called the contractive learning, right? I don't know if you guys know that. Basically, it says that they wanted the whole feature space actually compressed as possible. Then this work is sort of opposite. So actually, in the beginning, caused a lot of confusion, right? Should you contrast or should you contrast? Right. So of course, recently people started. This is the older paper, but recently people with better engineering, they kind of try to say, if I have feature points, right, 2 pairs of data points draw from the multiple class data sets with high probability they belongs to different classes. Hence, I only have to Z prime is just the augmentation of the ice sample. For example, rotated version of it. So those needs to be, the inner product needs to be large. The larger the better. Right? They want to be correlated. And also the inner product of features between different samples should be the smaller the better, right? So that's sort of a contrastive part. So but it turns out that this but it's, why do you choose this particular form? What this quantity means, nobody knows, right? But this is somehow people come up with, and then you use this objective function to optimize the Z theta, the neural network. It turns out to learn something reasonably okay. Now, let's think about what they're doing in the context of ReduNet or the rate reduction. They essentially says, if I don't have the class label, probably the best I can do is I treat every data points and its augmentation as one class. I try to expand them as much as possible. So that's the first term, this term. Basically, they want to occupy enough space so that I have a chance that different features, features from different classes are maximally separable. They are really emphasizing on this. But since they don't have the label, hence the compression is very weak. That's why there's a lot of finicky tuning, right? How many sample size, batch size, architecture, network, and how do you train even matters. You know what I mean, right?
So it's practically, really, they don't have the RC term.
No. Well, they have very weak one, right?
Weak one,
augmented one. Yeah, they basically that's the denominator, right? The Z and its own augmented version. The inner product needs to be large. That's it. Right. That's why they call it self-supervised already, right? But now we know. Also, this is also limited. It's only pairwise, right? But turns out now, from a compression point of view, we can compress any subsets if we know they're in the same subspace, the same class, or we can contrast the multiple class. We don't have to just do pairwise, right? So that's why you can see in the rate reduction, here you can have a K classes. Doesn't really matter. As long as you know a decent knowledge about they should belong to the same class, then you compress them together, right? And also when you do contrasting, this gives you a more rigorous measure of the volume of the feature space, rather than just inner product, pairwise inner product. Although, as I said, computing this precisely boils down to computing inner product, right? But this is a more holistic way, measuring the entire set for you, rather than just pairwise. Yeah.
Got it.
Yeah. So one good thing about this framework is start to really explain, all the different pieces, even different, partial approaches to make things work or not work.
Yeah. Well, thank you very much. This is the really, really great talk. And I also want to thank the audience for hanging on there for this 90 minutes lecture by you. We have some more comments and the questions from the audience. I apologize. We already run out of time. Before I give the floor to Professor Yao to conclude the lecture, I'd like to just repeat what I learned from you about this incredible joke. I think this is a takeaway from me and from your lecture, that all those mathematicians like Professor Yao, they actually say this different things with the same name. People like us that do machine learning, actually, we just with the same thing, we just want to understand that we actually have different names. Self-supervised learning, unsupervised learning, whatever supervised learning, it's all learning.
Yep.
So let me give it back to Professor Yao.
Okay, thank you.
Oh, well, thank you very much indeed. That's a really great talk. I think I learned a great deal. And I hope mathematicians will get into this subject much more. But indeed, a lot of people are using, deep learning and all that in their research in theoretical physics, in, theoretical mathematics in many ways. And I hope the future will be great. I mean, that we will all get into it and then we learn something from you. Thank you again for the beautiful talk. And it is, well, 2:30 here in China.
Okay, thanks a lot for having me. And also, it's also really a truly even extra appreciation for Yao and Harry stay up late. And also for the audience, if you have any questions about the work, you'll be happy to I'll be happy to answer your question by emails. Right.
Oh, I should also say, I should help Yi to promote in the beautifully written book, with John Wright, and I highly recommend everyone to get a copy of Yi's book.
Yeah, so this work actually becomes the last chapter. We developed this work actually when we were trying to really write the last chapter of the book. You probably get a better context of where the connection of deep networks and the low-dimensional structure are truly taking place. All right, thanks. Thanks for the.
Thank you very much.
Okay,
everyone. Stay safe.
Thanks again. Yeah. Bye.
Bye-bye.
Thank you. Bye.
Bye-bye, Professor Yao.
Yeah, thank you. You too.